This is our last chance to review for the final, not the final exam, but the last chapter exam of the semester. Chapter 18 on electrochemistry. And we're going to take version 2 of the review document. Yeah, version 1 is available, but I'm going to use version 2. And I think I've got time to go through the entire thing. It's a short review if I don't digress too much. So the last exam, this is going to be the review. Next week will be final exam week. And the scheduled exam is on the 6th. That will be the same day, same time, if you come in person. So let's get on with it. Number 1. Let's see. Make sure I got my marker. All right, for this reaction, sodium bromide with chlorine gas. Since this is a word problem, you got to know how to write the compounds and then put them in the proper place in the equation in order to finish your thoughts and answer the question. So we're going to react sodium bromide and chlorine gas. Number 1, sodium bromide and chlorine gas has to be diatomic, remember? And it produces sodium chloride and bromine. Sodium chloride and bromine. Now, we're not writing the phases in here. For one reason, none of the answers indicate phases. So I would take that to mean that it's not important in this case. The question is, write the appropriate half reactions, oxidation and reduction. And what that means is, when this is balanced, then the half reactions must also be balanced in order to add together and produce the balanced complete reaction. So let's take these as oxidation and reduction. So we've got to decide which species are being oxidized, which are reduced, and also account for the spectator atoms that may accompany the oxidized or reduced species. So the first thing you need to do is list the oxidation states. I start with the easy ones, right? Elementals, always 0. Bromine, well, sodium is an alkali metal, and the rules say that alkali metals are always +1. So if we do that, +1 +1, then the bromine has to be -1, chlorine has to be -1. And we already knew that because of the way we learned to write chemical equations, assuming that all alkali metals are +1, all halogens are -1. In this case, that's true. Okay, so now we know that sodium is a spectator. Right? So, and notice also that the only place that sodium occurs is here in this answer. And we know that one's wrong because sodium is +1 here and +1 there. No change. So it's not even part of the oxidation reduction reactions. So a half reaction for oxidation. All right, oxidation is loss. Who lost electrons? Well, it looks like bromine went from a -1 to a 0. If you go from a -1 to a 0, you have had to lose 1 electron. So we have bromine -1 yields Br2, 0. We'll just write those in there for convenience. And to lose an electron, the electrons end up on the product side. So we have 1 electron per bromine. But how many bromines are there? Well, there have to be 2. So that means 2 here means that we had to lose 2 electrons. Right. So there's the oxidation step. The reduction step would involve chlorine at 0. And reductions always have electrons added. So they're a reactant. And they're going to produce chloride ions. Okay. Here again, we have 1 electron per chlorine, but there are 2 chlorines. So that means we have to have 2 electrons. The other condition that has to be met is before we can add them back together and make a balanced equation, the electron numbers have to be equal on both sides of the equation. And they are in this case. So if we add these back together, we should get 2 of these and 2 of these. Okay, that would be the balanced equation. But of course, that's not the question. The question is, what are the oxidation and reduction half reactions? So we look for 2Br minus for the oxidation. All the oxidations are on this side. So 2Br minus, actually, this one should be it, because that's the only one with 2 bromide ions. Let's see if the reduction works. Cl2, 2 electrons, 2 Cl minus. That's the one. It's B. B is your answer. Okay? All right, let's move on to number 2, and I have to scroll that one. There we go. So number 2. Having trouble with my markers today. There's one. Okay, 2 says ammonium metavanadate. Okay, notice that there's no ammonium in that equation, right? That's because ammonium is a spectator. We don't need it. And it reacts with sulfur dioxide, which is there, in acidic solution and produces these products. Right? Okay, so what we want to know is what's the ratio of X and Y? Well, it looks to me like if the creators of this question say that that's an X and that's an X, then these values should be the same, and these values should be the same. So we have 2 choices. We could go through the entire half reaction balancing routine, balancing oxygens and hydrogens with water and protons. Or if we only go through the first few steps that balance the non-oxygen, non-hydrogen atoms, then we should be able to get that ratio right there. And the only thing that would change in the final balanced equation is the appearance of hydrogen ions for acidic solution and waters to balance the hydrogens and all the oxygens. So what that says is we really only need the first couple of steps. And that also tells me that I can use a simplified version of the balancing routine. And here's what I mean by that. So here's our starting equation. VO3 minus, and then SO2 yields VO2 plus and SO4 2 minus. So I'm going to use, like I said, an abbreviated version. So the oxygens are not going to change their oxidation states. Not in this case. These are all -2s for oxygens. So the players in this oxidation reduction reaction are vanadium and sulfur only. Right? So what happens to the vanadium? Let me get this out of the way. Let's say it's right over here. Okay, if we go for vanadium, we need to know the oxidation state for vanadium. So here we have a -2 for the oxygen, which means -6 total. But we need to hold out one of those negatives. So -5 is all that needs to be balanced, and that's +5 for that vanadium. For this vanadium, -2 for the oxygen, there's only one of them. But we need a 2 plus. So that means we need to balance a -4. And I'll prove it to you in just a second. That means this vanadium is +4. Okay? So the oxidation state of one oxygen is -2. If the oxidation state of +4 for vanadium, then a +4 and a -2 gives you a 2+ charge. Okay? In other words, I'm right. So if we go from a +5 to a +4, what process was required? We needed to add an electron. So reduction is gain. So we're going to gain 1 electron per vanadium. All right, now let's do sulfur. If this is -2 and -4 total, and we have a neutral compound, so we need to balance those -4 with a +4. So that sulfur is +4 oxidation state. We have a -2 for oxygen, a -8 total, but we need to hold 2 minuses out. Correct? Yes. 2 minuses out. That means we only need to balance -6. So this is a +6. All right. So now when we go from this sulfur to that sulfur, we have lost 2 electrons per sulfur. To go from a +4 to a +6, we had to lose 2 negative charges. So we lost 2 electrons per sulfur. Okay. So 2 electrons per sulfur, we need to balance the electrons. If 2 electrons are lost between these 2 positions, then we have to gain 2 electrons here. So we have to multiply by 2. So that gives us 2 electrons. How do we do that? We need a coefficient. We need actually 2 vanadium here. There. Okay. So now that gives us the 2 vanadiums, 2 electrons here, 2 electrons there for 1 sulfur. And the ratio then is X is 2. X to Y is 2, and Y is 1. Okay, that's why the answer is 2:1. All right, that was 2. How about 3? All right, following reaction occurs in an aqueous acid solution. In the balanced equation, the coefficient of water is, all right, now in this case, we have to go all the way, half reaction method, because it's asking for the coefficient of water, and there's no water there. But we do know that there are oxygens there. That indicates that water is going to be added somewhere to balance the oxygens. Okay, so first thing we have to do is take our initial equation right? Yields IO3 and NO2. Okay, we got to decide which one's oxidation, which one's reduction. So with, well, this one is a -1, right? That one's easy. It's the charge on the ion. Oxygen's -2, which is -6 total. Hold out 1. That means nitrogen is +5. Right? This one's -2 for oxygen, -6 total, 3 times 2. Hold out 1. This iodine is +5. -2 times 2 is -4. It's a neutral compound, so this nitrogen must be +4. All right, so now we have all our players identified and their oxidation states. We need to decide which one is oxidation. Let's give myself some more room here. Oxidation. Which one is reduction? Okay, oxidation is loss. So who lost electrons? Nitrogen to here actually gained electrons. Right? So this one, NO3 minus, let's just keep our oxidation states, yields NO2 +4, had to gain electrons. So that means what's left over, this iodine yields this iodate. That's a +5, and that's a -1. So that one had to lose electrons. Okay. All right. Now we balance the non-oxygen, non-hydrogens. So one iodine, they're balanced. One nitrogen, they're balanced. Now we balance the oxygens with water. With 3 oxygens on this side, we need 3 waters on this side. And then we balance the hydrogens. This is acidic solution, right there it says. That means we need 6 protons on that side. Okay. How about this one? We've got 3 oxygens on this side and 2 on that side. So we need another oxygen on the product side. Now we have 3 oxygens on both sides, but we have 2 hydrogens that have to be accounted for. Okay. Now we balance the electrons. All right, so if we're going to go from a -1 to a +5, how many electrons did we actually lose? Well, lose 1 electron, you're neutral. Then lose 5 more, and you're +5. So 1 and 5 is 6. Those are the 6 electrons that were lost with this equation. This one only requires that you gain 1 electron to go from a +5 to a +4. Okay? Now we've got the individual half reactions balanced. We need to reconcile differences in electron numbers. So if this one has 6 electrons, we need 6 electrons here. So 6 times the whole equation will give us what we need. So now we have 6 here, we have 12 here, we have 6 there, 6 there, and 6 there. Now we can add them together. But we can go ahead and do that, but if you're taking an exam, you want to work efficiently. So what's the question? What's the coefficient of water? All we need to do is add the waters, right? We have 3 waters here. And on this side, we have 6 waters. Okay, so these 3 waters go out, and we have 3 left over. So the coefficient of the water is 3. And we saved ourselves the trouble of writing the entire equation just to find water. We've got all the information we need here to answer the question. That was 3. All right, scroll to get number 4. All right, now we have one. This reaction occurs in basic solution. So how do we do that? When the equation is balanced, the sum of the coefficients, that means we do have to go all the way. And we have to make the final conversion into basic solution. So we're going to use our fake acid method, as I call it. So here's our starting position. F2 plus water yields O2 plus F minus. Okay. 0 minus 1. This one is -2. This is +1. And this is 0. Okay, this one should be fairly simple. Let's see if I'm correct. We noticed that oxygen goes from -2 to 0. So in this case, oxygen is part of the reaction, the redox part of the reaction. So the oxidation step, reduction steps are, we're going from, let's take oxygen, -2 to 0. That means each oxygen lost 2 electrons. So we're going here, water at -2 is going to O2 at 0 and to lose 2 electrons, right, for each oxygen. Well, I'm getting ahead of myself, but that's okay. And let me be consistent. Let's leave that till later. That's the oxidation step. The reduction step is this one, fluorine gas, fluorine ion. Okay, this one had to gain electrons. Okay, so now we know we want to balance everything that's not hydrogen and oxygen. For this one, there's nothing to balance. For this one, we need 2 fluorines. Okay. Now let's balance the hydrogens and oxygens, right? There's nothing to balance here, but we do need, if we're going to have 2 oxygens here, we need 2 oxygens here, but that gives us 4 hydrogens. Okay. Now we can go to the electrons. This oxygen goes from -2 to 0, which means it lost 2 electrons per oxygen. But there are 2 oxygens. So if it loses 2 per oxygen, that means it lost 4 electrons. Okay. On this side, we went from 0 to -1, which means it gained 1 electron per fluorine. But we have 2 fluorines. So we actually gained 2 electrons. Okay. So now let's balance the electrons. We need to multiply this one by 2. So that means a 2 here, 4 there, and 4 there. So our electrons are balanced, 4 and 4. Okay. When we add it together, we have 2 fluorines plus 2 water, 1 oxygen, 4 hydrogens, and the electrons cancel. Okay, that's an acidic solution. Now we want to adjust it for basic solution. So how do you do that? You add hydroxyls. How many? Enough to neutralize the hydrogen ions. We have hydrogen ions here. So if we're going to do anything to one side of the equation, we have to do the same thing to the other side. So in order to neutralize these hydrogen ions, we need 4 hydroxyls. But we also need 4 hydroxyls on this side. Okay? This makes 4 waters. Right? And we have 2 waters on this side, 4 on this side, which makes 2. Okay. Now we should be balanced. Coefficients. 2 plus 4 is 6, 7, 8, 9. Why does it say 13? Hold on a second. 2, 6. I left something out. Yes, I did. 4 fluorines. There we go. 9 and 3 and 4 is 13. So there we go. Attention to detail. All right, that was number 4. Let's see if I can do this. There's 5. Let me see how many problems we've got. If I can really get all these done in one day. Yeah, quite a few. Might have to start skipping a few. For now, we'll go ahead and do them one at a time. This reaction occurs in basic solution. In the balanced equation, what's the sum of the coefficients? So here's another one where we have to balance and add up. Let's see. Yeah, I think I will do this one. Because this one starts off with hydroxyls. Okay, so we're beginning with zinc, nitrate, and that yields zinc, hydroxide. Actually, this is a complex ion. And then with ammonia. Okay. Oops. There we go. Okay. Oxidation states. 0, -2, -6. We need to hold one out, so that's +5. Okay. Hydrogen's +1, so that's +3 total. That means -3 here. How about this one? If we want to find out what zinc is, oxygen's -2, hydrogen's +1. Right? So there have been no changes with the oxygens or the hydrogens. So what's the charge on a hydroxyl ion? The hydroxyl ion is a -1. Right? -1. There are 4 of them. Right? So if it's a minus, +2. Hydroxyl minus with the oxidation state there. That means the reduction had to be the nitrate at +5 here and minus 3 there. Okay. All right. Okay, so let's balance the non-oxygens, non-hydrogens. Zinc, one zinc, we're good there. One nitrogen, we're good there. Now we can go to the oxygens. We've got how many oxygens here? We have 4 oxygens. So we need 4 waters. Okay? But we've got now 8 extra hydrogens. So how many hydrogens do we need on that side? We've already got 4. We've already got 4 hydrogens. Right? So we only need 4 more hydrogens. Right? 4 plus 4 is 8, and then 4 oxygens. Now we're good. How about this side? Well, oxygens, we need 3. There we go. Now we have 6 hydrogens plus 3 is 9 hydrogens, correct? Okay, now we can do electrons. The oxidation state means we need electrons over here. How many? Well, we need 2 electrons per zinc. And there's only 1 zinc. So we're done there. Here we have plus 5 to a minus 3. How many electrons had to be added? 5 electrons will take you to 0. Then 3 more electrons. So that's 8 electrons per nitrogen. And there's only 1 of them. Okay. Now, we need 4 times this will give us 8 electrons. 4 there. 4 times 4 is 16. 4 there. 4 is 16 and 8. So now the electrons are balanced. Now we need to add all this together. So we have 4 zinc. We have, let's just keep it in order. 16 water, 1 nitrate. Let's see, I left the charge out of that one. Yeah. 9 hydrogens. Electrons cancel. And this side, 4 of this complex ion. And 16 hydrogens, and then an ammonia and 3 waters. Okay, 3 waters. Okay. So if we combine things, we got 16 waters here and 3 over here. So we can do away with those, and that makes 13 waters here. Now we have 9 hydrogens and 16, so these 9 go away, and now we have 7. But we're still acidic. All right, so we need to neutralize these 7 hydrogens. Like that. Okay, so what does that give us? Well, that gives us 7 waters, right? There we go. But we got 13 on this side. So those waters go away, and now we're left with only 6 waters. And 7 hydroxyls. Okay. All right. So we should be balanced. 4 zinc, 4 zinc. Let's see. 12 hydrogens. 7 and 12 is 19. So we have 16. 19 hydrogens. There we go. Oxygens. We have 6, and 3 is 9, and 7 is 16 oxygens. So we have 16 oxygens here. That's it. We're good. Okay, so now we can add the coefficients. We have a 4, a 6, a 1, 7, 4, and nothing there. A 1 here, and that's it. So 4 and 6 is 10, 11, 18, 22, 23, 23. So there we are. Coefficient is 23. That took some doing. And be very methodical and careful about it. One thing that might have thrown you, if you see one of these types of problems for the first time, is we're told that it must be in basic solution, right? And you see these hydroxyls right here saying, well, that's already basic. Maybe it is and maybe it isn't. Because these hydroxyls are combined in a complex ion. They're not out floating free in the solution. So we have to just follow the procedure. Balance it by for acidic conditions, and then neutralize it with hydroxyls, and we're good. Okay, let's see, 6, get this one without scrolling. The last one is none of these. So let's see, when the following reaction is balanced in a 6 solution, what's the coefficient of iodide? All right. So we're starting with iO3 minus plus I minus yields I2. Okay. Oxidation states, -2, -6, -5 to balance, +5. Okay. Oxidation step. Who lost electrons? If we go from this one, notice this is a disproportionation in reverse. Right? We've got one iodine over here, it is split into 2 positions over here with different oxidation states. So how do you deal with that? Well, this one to here is reduction. And this one to here is oxidation. Oops, excuse me. That one to there is oxidation. So the oxidation step is going to be iodide yields iodine. And the reduction step is going to be iodate to iodine. All right. Okay. We've got 2 here, we need 2 there. Okay. We've got 1 here, we got 2 there, so we need 2 here. Now we have no oxygens up here, no problem. We have oxygens here, we need 6 oxygens on this side. Which means, by the way, yes, this is acidic solution. So we have 12 hydrogens. reduction. Should have given myself some more room, shouldn't I? Okay. Yeah, we can go ahead and do electrons now. Reduction means we need to add electrons. So how many electrons does it take? Well, we're going from +5 to 0. So we have to add 5 electrons per iodide, but there are 2 iodides. So we have 10 electrons added. In this one, we're going from a -1 to a 0. We lost 1 per iodine, but there are 2 iodides. So we have 2 electrons. All right, to make 10 electrons, we need to multiply this one by 5. So that makes this one 10, 5, and 10. Okay, now that our electrons are balanced, we can add them together. So we have 10 iodide ion, iodide, that's correct, plus 2 iodates, plus 12 hydrogens. Electrons are gone. Yields 5 iodines plus I2 plus 6 waters. Okay. So now we need to combine these two, right? 6 I2. There we go. Now let's see if that adds up. And let's see, we have 2 plus 10 iodines is 12 iodines. So we have 6 times 2 is 12. 12 iodines. We have 6 oxygens, and we have 12 hydrogens. So the numbers balance, and we know the electrons are balanced because our half reactions were balanced. Okay, what was the question? What's the coefficient of iodine? 6. Hold everything. Here's one thing that we didn't talk about much in class. I may have mentioned it, but if we're going to write the equation in its simplest form, we need to see, is there a divisor that will go into each coefficient a whole number of times? So if we've got 6, 6, 12, 2, and 10, we can divide each one of those by 2. Right? So this would be 5. This would be 1. This would be 6. This would be 3. And this would be 3. So the coefficient of iodine here is actually 3. Okay, that's one of the tricks for this one, is simplify your equation. All right, that was 6. 7. All right. We've done one of these before. For the redox reaction here, which of the following are the correct half reactions? Out of these selections, which ones are the correct ones? You know, maybe we better take a look at that one. It's saying that this one is balanced. Let's check it to see if it is. Let's see. 2 chlorines. Oh, I left this one. 2 ions. Okay. But this one is 0. That's -1. So what have we got? We've got a gain of 2 electrons. Or 1 electron per chlorine times 2 equals 2 electrons. That means this one had to lose 1 electron. 1 electron per ion times 2 equals 2 electrons. Okay, so the electrons balance on both of them. And this one, the trick here is to simplify. Right? This one is the reduction. Right? So which of the following correct half reactions? The reduction is going to be, let's see, 2 electrons. Here we go. Chlorine plus 2 electrons yields 2 chlorides. This one, 2 electrons. There. All right. So what's the oxidation step? Well, the oxidation step is going to be Fe2 plus to Fe3 plus with 1 electron lost. Right. So the trick to this one is that what are the oxidation and reduction half reactions before you balance the equation? I think that's what's being asked, because this is the simplified version. Right here, here to here. Without the coefficient. Now, you could not add these 2 together, right? Because that has 2 electrons, this only has 1. But the half reactions are written correctly before you complete the balancing routine. Okay, 8. Let's see, do we want to do 8? How many electrons are transferred in the following reaction? Yeah, we can do that one. We really do need to do something like this because what do we need to know if we're going to determine the electromotive force, the voltage of a standard cell? Well, actually, not the voltage of a standard cell, but the voltage, the actual voltage of a cell. Besides knowing the concentrations, let's see. Besides knowing the concentrations of our reactants, we also need to know how many electrons are transferred, because the Nernst equation requires knowing how many moles of electrons are transferred in the process. So we'll take this equation and find out how many electrons are actually being transferred. Now, are we assuming that this equation is balanced? More than likely. We can check it to be sure. Let's see, 2 chlorines. Let's see, 6 Oxygens, yep, 6 oxygens, 12 hydrogens, 12 hydrogens, 10 iodides, 10 iodides. So the equation is balanced. So let's decide what happens to who? 0, 0. Hydrogens and oxygens don't matter. -2, -6, -5, +5. Okay. And let's see, I must have left off. Yeah, I did. Okay. So we're going from a +5 chlorine to a 0, which means we have to add electrons. So I actually gain 5 electrons per chlorine times 2, which is 10 electrons. Okay? This iodine is going from here to here, and it lost how many electrons? It lost 1 electron. Lost 1 electron per iodine. But we have 10 iodines. 10 electrons. Okay, so how many electrons are transferred? 10. Right? If somebody loses electrons, somebody has to gain those electrons. Oxidation reduction always occurs in pairs, and the same number of electrons are gained as lost. So that's why the answer is 10. Let's see. I'm going to have to scroll that one a little bit to see if we even want to tackle this one. If it's got some new information, we'll stop here and do this one. Let's see. Balance this equation in basic solution, and then sum the coefficients. I don't think there's anything special about this one. You do have oxygen in one place here for this manganese. There's one there and there's one there. And then for the cyanide, you have an oxygen here. So you're going to have water balancing for both oxidation and reduction half reactions. But there's nothing special about this one. I'm going to leave this one. And let's move to the next one. The number of electrons transferred during this reaction when balanced. Okay. I think we can do this one pretty quick. 10. The reason I say that is there's no oxygen, there's no hydrogen. So we don't need to use the complete half reaction version. We can do the abbreviated version. And here's how it looks. This is a polyatomic, no, not polyatomic, a complex ion. Okay? So we have, let me write it down here like this. AuCl4 with a -1 charge, and then copper. Okay, this is aqueous. That's solid. My guess is this is an electrochemical cell, a galvanic cell. There's one electrode. Here's the other electrode. Aqueous and aqueous. All right, so what's happening here? Well, this one's 0, this one's 0. What about this one? In this case, we're going to have to assume that this halogen is -1, which makes this gold. Let's see, -4, have to hold out 1, is a +3. Right? That should be equal. -4 + 3 is -1. Over here we have -1 chlorine and a 2+ copper. Okay. So what's changing? The chloride didn't change. It went from a -1 to a -1. So that's a spectator. This gold went from a +3 to a 0. So it had to gain 3 electrons per gold atom. And the copper had to lose 2 electrons, right? To go from a 0 to a +2, 2 electrons per copper. Okay? We're going to say this chloride balanced. When we balance the equation, actually the number of electrons transferred we can do without balancing these chlorides because they're spectators. Doesn't matter. So if we've got 3 electrons for gold and 2 electrons for copper, how do we reconcile an odd with an even? Cross multiply. So this 2 becomes a multiplier for this group. That means 2 golds here, 2 golds there. And then times 2 equals 6 electrons. Then times 3 equals 6 electrons, which means we need a 3 here and a 3 here. Okay? So the number of electrons transferred in this reaction is 6 electrons. And we didn't even have to balance the rest of the equation, right? 8, if we wanted to, there'd be an 8 here, right? 8 chloride ions. And the equation is balanced. So that's my shortcut or abbreviated version of half reactions. When you don't have oxygen or hydrogen need to be dealt with. Okay, number 10. Let's see how we're doing on time. 9 o'clock, and we're good till 10:50. Oh, we don't have a lab today, so I can take all the time I need to finish these out. Let's see, how about 11? Consider a galvanic cell based on the reaction here in acidic solution. Calculate the voltage of the standard cell carrying out this reaction. Okay, so we don't have enough information there to do the standard voltage, right? We need a table, and that will come at the end in useful information. But we need to know which reactions are responsible. All right, so let's write the overall equation and then pull out the half reactions, one for the cathode, one for the anode. And dichromate, okay, and Fe3 plus, and chromium 3 plus. Now I have to assume that these are all in an aqueous solution here, which means what? The electrode that goes into each one of these half cells must be inert. It's not a participant in the reaction. Okay, so oxidation state, oxidation state, oxidation state. How about this one? -2 for oxygen, -14 total, but we have to hold 2 out, right? -12 means +12 here, but each one has to be a +6. Okay, so now we know the oxidation step, or what? What's the oxidation half cell called? The anode. And the reduction half cell is the cathode. Okay, so this one is the oxidation step is here. This iron 2 plus was changed to 3 plus with 1 electron. And This one, CR2O7 minus plus 6 here, went to here. Okay. Now, do we need to balance those equations? Well, let's see. What's the standard reduction potential? Oh, excuse me. I forgot. Electrons. 2 chromiums here, 2 there. And we have a plus 6 going to 3 plus means we have to add 3 electrons per chromium, but there are 2 of them. So 2 times 3 is 6. 6 electrons. This, they want to know the standard cell. So it doesn't matter if they're balanced for electrons. These are standard conditions. So all we need is the standard voltage. So the reduction potential for this one, we need to go to the end of the document. So let's go down to the end. We'll eventually get there. I might have to skip a lot of them to finish today. And more. Here we go. All right, this one slid off the page for me. All right, hold on a second. No, it won't shrink anymore. Okay. All right, rather than take up time, the standard reduction potential means that this one is in reverse. We're going from 3 plus to 2 plus iron. So let's see if we can find that one. 2 plus iron on this side. 2 plus iron, 2 plus iron, 2 plus iron. Nothing there. How about here? Iron. Here we go. No, that's 1 minus. Oh, that's a metal. So let's keep going. Nope. All right, let's keep scrolling. Iron. Here we go. So this one was Fe3 plus an electron is 0.77. So the standard potential here is, standard reduction potential is 0.77 volts. But that's for this direction. We're going to go this direction, so it needs to be a minus 0.77. This one is already written reduction. So we just find that. Chromate to chromium 3 plus. So let's see. Go back up. Chromium 3 plus. Here we go. I think this is the right one. Let me check it in a document where I can actually see it. Yes. That's the right one. So it's right, where was it? Here, right here. That's 1.33. Okay, add those together. Okay. Let's see. 7 and 13 is 6. And 7 is 5. Anyway. Plus 0.56 volts. Let's go back. Number 11. Oops. I got out of sync here. There we go. So the standard potential for this cell is plus 0.56. There it is right there. All right. Okay, that was number 11. Let's see. About number 12. Which of the following reactions is possible at the anode of a galvanic cell? The anode requires oxidation, correct? Okay, oxidation. And it must be a half reaction. Right? This complete reaction, it could be true for the whole cell, right? The whole galvanic cell could be that, or it could be this one. But those are not half reactions. This one's a half reaction, but it's a reduction. This one is the only one that satisfies, and let's be sure, which of the following could be anode? Zinc is 0 to 2+, which means it had to lose 2 electrons. That's true. A. That could be an anode. So you have to remember the definition of an anode and the requirements for writing the half cell reactions. Right? You can't use the whole balanced equation to define an anode or a cathode, for that matter. All right, that was 12. I'm going to start skipping now. Let's see. Well, maybe not skipping. How about 13? 13 looks like a good one. The anode in a voltaic cell and in an electrolytic cell, right? This is important distinction. Actually, it's not distinction, it's commonality. Whenever you talk about an anode, whether it's a galvanic cell or an electrolytic cell, right? Whether the electrons are spontaneously moving or they're being forced backwards, doesn't matter. Whichever cell describes oxidation, that is the anode. So the anode in a voltaic cell and an electrolytic cell is the site of oxidation and reduction? No. Site of, no. It's only oxidation. In either cell, oxidation is defined, well, it is renamed anode. So that's why D is the correct answer. All right. Let me scroll this one. We may do this one, I'm not sure yet. Actually, I'm going to skip down to 17. And I have to scroll. I hope I can get it all on the same page. No. Consider the galvanic cell shown below. And the contents of the cell are described below. So this solution, in addition to the chromium metal, this solution contains 0.2 molar chromium 3+ ion. This one has a platinum electrode, which obviously does not participate in the reaction. But it does have 0.5 molar bromine and 0.1 molar bromide in that solution. So the half reaction is between bromine and bromide. And the platinum just serves as a conductor of electrons. The standard reduction potentials are as follows. Here we go. All right, so let me scroll just a little bit. Let's see if I can get, yeah, we got them all on there now. The standard reduction potentials are as follows. What is the standard EMF? What is the standard voltage for this cell? Okay, let's see if it's written correctly first. Right? So this cell, the reduction potential for this cell is minus 0.727 volts. Well, that depends on whether it's the anode or the cathode. If it's the cathode, yeah. And typically the cathode is written on the right-hand side, but maybe not. Let's check it out. This reaction is bromine to bromide with that potential. Okay, that looks fair. Actually, we don't need to say which is which. All we need to do is say what combination will give you a positive answer. Well, they can't both be reduction. One of them has to be oxidation. So let's say, what if we make the first one oxidation? Just flip it. That makes this one positive, that one positive. That gives us a positive voltage. Right? So that's probably right. If we flip this one, it makes that one negative, and now they're both, the summation is negative, so that can't be it. So this one is the anode. Right? So this one's written backwards to our convention. Right? The electrons actually flow this direction. So if we write this one backwards, that makes this positive and this one positive. Add them together, you get 1.817. 1.817. Right there. A is the answer to this one. We have to convert this one. We have to flip this one and make it an oxidation or the anode. In order to make that one positive, add it to this one, makes it positive. All right. Let's see. Do we want to do 18? Okay, let's look at that one. So here we have another set of half cells in our galvanic cell. And we're given the standard reduction potentials for each of the reactions. I need to scroll now. What's the standard potential for this one? Did I say that was 18? I would use the same line of reasoning as number 17. If you're only looking for the standard potential, you just need to take these voltages and say, all right, which way will give me a positive value? If I make this one negative and add that one, that's a positive value. So this one has to be flipped. This one has to be reversed. So that's the anode, this is the cathode. And if we do that, that will give us 1.506 and then minus 1.33067 plus 0.176 volts right here. Okay. Now, if we're looking for the actual voltage, right, we need to consider these concentrations, and we also need to write the balanced equation. We need to know the number of moles, and we need to know the Q for the equation, in order to use the Nernst equation. And the Nernst equation is given to you in useful information, so you don't have to memorize it. Let's see. This looks like the same cell. Must be a different question. when the current is allowed to flow, which species is reduced? Okay. All right. Remember, let's see, this was number 19, right? 19. Remember, we reversed this one. So that means it was an oxidation. So the reduction we want to look at is up here. Which one of these is reduced? Right? Well, the manganese changes its oxidation state from, let's see, what is it? Or a 7, +7, right? +7, and it's going to 2+. So we have to add electrons of a certain number. So that means this one, MnO4, has to be reduced to answer that question. Which is reduced? Because that is the cathode. All right. Let's see. Do I want to do 20? We might look at 20. All right, let me scroll it up. There we go. All right. Same reaction as before. So we already know which one is the cathode, which one's the anode, which one is the reduction step, which one is the oxidation step. All right. So if we're going to do that, we've got to combine the equations because you can't write the Q for half reactions. You have to write the Q for a balanced equation. So if we take this one as the reduction step, let's see, reduction, yes, this is the reduction step. That's the oxidation step. Okay, MnO4 minus plus 8 hydrogens plus 5 electrons equals Mn2 plus 4 waters. And you don't need the standard voltage now because we know which direction they're going. And the question asks you for Q, doesn't ask you for anything else. So oxidation then would be the other one in reverse. So we have 2 chromium 3 plus 7 waters. And that yields dichromate ion plus 6 electrons. Okay, so now we need to combine these equations. You've got 6 here and 5 there. Right? These are balanced half reactions. Now we need to rearrange them to, we need to modify them so that we can combine them. This is a 6, that's a 5. I multiply this one by 5. And this one by 6. So now we have a 6 there. We have a 48 here. We have a 30 here. We have a 6 there. And we have a 24 there. Now we have a 10 here. We have a 35 there. We have a 5 here. We have a, let's see, 5 times 4 is 20, and 2 and 5 is 70 there. And we have a 30 here. So we have the same number of electrons. we can add our equations together. All right. So let's see. We have 6 MnO4 minus. I'm going to do the major species first. And we have 10 chromium 3 plus. Now we have, let's see, bring down 6 manganese. Let me underline these so I've got them. We've done that one. We've done this one. We've done this one. Now I want to bring down this one. CR207. Okay, we've done that one. Now let's see if we can simplify hydrogens. Hydrogens here, hydrogens there. 48 from 70 is 2. Yeah. 22 hydrogens. 22 H plus. There. Okay, we've done that one. We've done this one. How about waters? We've got 24 waters here. And we've got, that makes 11 here. 11. Oops. 11 waters. There we go. Done that. So it looks like we've covered everything. All right. Now, concentrations. This one doesn't matter. Pure water doesn't matter for the cube. Hydrogen ions do matter. All right, so what is the Q expression? The Q expression is this to the 6th power, this to the 5th power, and that to the 22nd power in the numerator. Right? So we have manganese 2 plus. Actually, that's not right. This is a Q value. It's not equilibrium. By the way, if it were equilibrium, what would the voltage be? A 0. Like that. So that manganese is to the 6th power. This dichromate is to the 5th power. And these hydrogen ions are to the 22nd power. Okay. Then in the denominator, we have manganate to the 6th power. We have chromium 3 plus ion to the 10th power, and no waters. Okay? So now, what's the Mn2 plus concentration? There it is, 0.2 molar. 0.2 to the 6th power. What's the dichromate concentration? 0.3 molar. 0.3 molar to the 5th power. And the hydrogen ion concentration? Well, it's 0.01 molar, right? Yeah. 0.01 molar to the 22nd power. Okay. Notice that it's the same on both sides. I'm not sure what we would do if it was different. But it's on both sides. So it's a non-starter. That's the value. NaO4, 0.1. 0.1 to the 6th power. And chromium 3 plus, 0.4. 0.4, 0, 10th power. Okay, that's the Q. Now all you have to do is take the 6th power of that one, 5th power of that one, 22nd power of that one, multiply them all together. Then take the 6th power of that one and the 10th power of that one multiplied and divide that product into the answer for the first one. And you should get 1.5 times 10 to the minus 41. Right here. So that's the Q. Let's see if I want to do this. Yeah, let's do this. Suppose we wanted to find out what is the actual voltage for that cell. We know the standard voltage, right? We got the standard voltage before. It was, let's see. I'm checking my values here. 0.176. Okay. And we know the Q is equal to that value. So how would we find out the actual voltage? Well, one piece of information we don't want to let get away is the number of electrons transferred, 30. N equals 30. 30 moles of electrons. Okay, now that I've got all that information, we can take this out. I wonder if there's a number associated with this. Is there a problem like that? I think 22. Is the same cell. Yeah, 22. 21 is the hydrogen ion concentration, which is 22. Right here. That answers that one, D. For 21. For 22, we want to calculate the actual voltage for this cell. So we know this one, that one, and the Q, 1.5 times 10 to the minus 41. And now we can erase all this and look up the Nernst equation because that's what we're going to be needing. Which is the actual voltage equals the standard cell minus remember that value, 0591. 0591 divided by number of moles of electrons. Yeah. Times the log of Q. Okay, so the actual voltage is equal to this one minus 0.0591 over 30 times the log of 1.5 times 10 to the minus 41. So what is the actual voltage? Here we go. Should be 0.26 volts. So with those concentrations, we've actually increased the voltage potential for this cell from 0.176 under standard conditions to 0.26 under these specific conditions of concentration. All right. That was 22. Let's see. Well, I'm looking to see. How much time we have. Got a little bit of time. This one should be fairly simple. For 23, consider an electrochemical cell with a zinc electrode immersed in 1 molar zinc 2 plus and a silver electrode immersed in 1 molar silver plus. These are the standard reduction potentials. And notice that those are standard concentrations right there. Okay. What they don't say is the temperature. And the temperature does matter. The original, the complete Nernst equation takes into account the temperature of the cells. The version of the Nernst equation that we used assumed that the temperature did not change. In other words, it was standard, 25 degrees Celsius. But the concentrations are standard concentrations, 1 molar, 1 molar. So all we have to do is decide, all right, which one is the oxidation, which one's the reduction? Which one's the oxidation? Anode. Which one's the reduction? Cathode. Cathode stays the same. Reduction. So if this stays the same, and we make this one the oxidation, that makes this one positive, and now we have a positive value, which means that's the direction. From cathode, actually electrons will flow from anode to cathode. And the value would be 0.755 and 0.800. $1.555 volts right here. Okay. All right, let me see. Do I want to mess with 24? Standard cell potential for 24. That's the same. That's what we've been doing all along. Let's see. Standard cell potential for 25. No big mystery there. All right, now we're getting into, let's do 26. Many freshman or beginning chemistry courses will teach this concept in terms of activity series. So when you look at that standard reduction potential, what you see is a list of reduction potentials. So if you're going to say, which one will spontaneously reduce which of the following? If copper spontaneously reduces something, copper must be oxidized. Right? So if we look at, well, if I scroll down to that table, it's going to be chopped off and that would be a mess. So let me try it this way. Let me just turn to that table in the review document and talk about it on screen. You'd probably see it better anyway if I do it this way. Okay, so let's see. I don't know, that's pretty small stuff. Let me see. Copper will spontaneously reduce. So if we're going to say that copper reduces something, that means copper has to be oxidized. In other words, it has to lose electrons and become something else. And for copper, that would be, see, I think copper is probably, hold on a second. I think it's a 2+ ion, generally speaking. I'm pretty sure. Let's say for the sake of argument that. So this particular value, the potential here is going to be the reverse of the reduction potential for copper. So the reduction potential for that step is 0.34, which means minus 0.34 would be the standard voltage for that one. So which one will it reduce? Well, whichever one that you can add and give you a positive value, right? So if we go to anything on this table underneath copper, they're either smaller, right, and will give you a negative value when you add them on there, or they're negative and you would add them. So anything below this one, it will not serve as a reducing agent. It has to be something above copper on this chart. So we look at the possible ones. Iron 2+, silver. Okay. Iron 2+, can we reduce iron 2+? No. Iron 2+ is negative 0.44. So we need a reduction. So iron 2+ plus electron yields iron metal. Okay? That won't work. How about aluminum? Well, how about silver? All right, let's find silver. So we want to reduce silver. What's the value here? 0.80, positive. So this positive and that value gives you a positive. So it will spontaneously reduce silver. Copper metal will reduce silver in solution to silver metal. So the short version of that is, under standard conditions, if you want to know which metal will reduce which other metal, which one will actually oxidize itself to reduce another element to its metallic form, you look above in the chart. So you look up here and then you go back down here and look up like that. And that's the simplest way. And silver is the only one out of that group, right? Aluminum will work. Aluminum is negative 1.66. Standard volts. So aluminum, 3+ electron. Right? So that won't work. Because if you add this one to that one, it's negative. Add this one to that one, it's negative. Add this one to that one, it's positive. So copper will reduce silver ions to silver metal. There you go. And that would be, the only other way to deal with this is to memorize an activity series. where you rank the metals on down the line, and this one will reduce anything above it, or anything below it will reduce it. But we didn't learn it that way. This is the logic behind the activity series. All right. So let me see. Where were we? We can do the same thing for this one. Right? Of these three, which could be reduced by copper, and you just look at them in your standard reduction potentials, and you say, which could be reduced by copper, and you say, okay, there's copper, look above it. Which one of these do you find above it? Silver is the only one. Which one of the following is the best reducing agent? Aha. Get rid of that thing somehow. 28. So which is the best reducing agent? Well, in order to be a reducing agent, you must be oxidized. The reducing agent is oxidized. So let's just put them in order here. Well, the way they're listed anyway. Magnesium, D, and E. Okay. So the best reducing agent is the one that is oxidized. So we would have to go here, here, like that. Or here, here, like that. Let's see, 2, yeah, 2, and 2. This one would be, magnesium would be 2+ because it's an alkaline earth. Right? This one won't give up any more electrons because you're into the core. Remember? The s electrons have already been, let's see, magnesium is 30. The 3 s electrons are already removed. You're into the core. That will never happen. This one, maybe. Right? You could go to this, and like that. Oops. No, wait a minute. That won't happen. Right? You would have to go to this. My mistake. To lose electrons, you'd have to do that. Right? And on principle, the halogens prefer to gain electrons, not lose electrons. So losing electrons counts that one out. This one is out. This one, maybe. So how do we tell which one is which? Well, we find out which one produces the smallest negative value. Because if it's the smallest negative value, then when you add it to a positive value, it's going to, the chance of going negative is. Let's look at it the other way. What are the standard reduction potentials for these? Let's just get that information first. The standard reduction potential for hydrogen ions, well, that's 0. Right? This is the standard electrode. How about this one? Magnesium. Magnesium. Need 2 plus, magnesium 2 plus. I'll find it. Here it is. Minus 2.37. And then chloride ion. Well, I want reduction. Chlorine plus chlorine. Here we go. That's 1.36. Here we go. Okay. What we're looking for is the largest positive value, because positive, even for half reactions, positive electromotive force implies spontaneity. Right? So this one's going to be 0 no matter what. But if we convert this one to oxidation, that makes it positive. Convert this one to oxidation, makes it negative. So the largest value in here is this one. That would be the best reducing agent because it is the most positive oxidation step in combination with any reduction. Okay, that's 28. Let's see here. This is interesting, 29. We have a line notation for a galvanic cell. All right. So here's the way the line notation looks. Sodium solid, phase separator, sodium ions in solution, bridge or porous, whatever. And we have copper 2 plus in solution, and then phase difference. There we go. Now, remember when we write line notation, the cathode's always on the right and the anode's on the left. So that means the electrons are flowing from this side to, let's see, this side. Well, actually, they're coming in this side here, like that. The electrons are flowing that direction. Okay? So the balanced chemical equation here would put the sodium, well, how many electrons are flowing? Right? If we're going to extract 1 electron from this sodium, right, and make that ion, but over here, we're going to add 2 electrons and go that direction. Well, adding 2 electrons to this makes that. So what are the half reactions? I think this is the best way. Write the half reactions first. So if we're going, if we're losing electrons, this is the oxidation side, the anode. There we go. So the anode is going to lose electrons, right? There we go. And the reduction side is the cathode. And that is gaining electrons. So we're going copper 2 plus electrons yields copper metal. Okay? So how many do we need? Well, actually we need 2 here. Okay. we've got no oxygen, no hydrogen to deal with. That's good. So now all we have to do is balance the electrons. So we need 2 here, 2 here, 2 there. The electrons are balanced. Now we can add it together. 2 sodium, solid, plus copper 2 plus aqueous yields 2 sodium plus aqueous plus copper solid. Okay? So that should be our balanced equation. Let's see, 2 sodium, copper 2 plus, 2 sodium plus, there it is right there, E. All right. Let's see, does 30 have any redeeming qualities? Let's see if we can get back to that page. All right. This is sort of a trick question, so I guess I should look at it. 30. The following reaction has a cell potential of 0.92 volts. Okay? So we've got 2 mercury 2 plus, and that's aqueous, then hydrogen gas yields 2 H pluses, and Hg2 plus aqueous. Okay, there's our balanced equation. Right. If the concentrations of the ions were 1 molar, so this is 1 molar, this is 1 molar, this is 1 molar, and this is 1 atmosphere pressure. Then what's the standard potential for this half cell? What's happening here? This 0 is going to a plus, which means oxidation. So that means this one is being reduced. Okay, and this is the equation for that reduction. Okay, what would be the standard potential, the standard reduction potential for that cell? Well, the other half cell is the standard hydrogen electrode, right? So the voltage for this one is 0. That means the voltage for this one would have to be 0.92 volts. Right? That goes back to the definition of standard reduction potential. It's standardized against this electrode here to here. This one to that one, which is taken as 0. Okay, so that's sort of a trick question, but it tests whether you recognize the standard hydrogen electrode in this situation. And that means that the voltage for that half reaction must be the same as the cell. All right, let's see. That's nothing new. Understand. the strongest reducing agent. Okay. This is like the previous question where we were trying to decide which one is the best oxidizing agent. No, the best reducing agent. Yeah, it was the same concept. So we need to say which one of these gives you the largest positive oxidation voltage. You just flip them all, right? 0 plus 293 minus 287 plus 166 and plus 0.313. The largest positive is this one right here. That K would be the strongest reducing agent because it is the more positive oxidation step. Right? So that's why K is the answer to 32. Let's see. Does 33 have some redeeming qualities? Which of the following statements is true concerning the electrochemical cell depicted below? So this is the anode, that's the cathode. Electrons are flowing from this end and going right here and coming in that end. All right, and these are the standard reduction potentials. Right? This one is for the anode. Notice where it's located. Right? That says reduction, but this side says it's oxidation. So you flip that one. And now it's a positive 2.87. Now, is the reaction spontaneous? If it's written that way, then this value becomes positive 287, and we add the negative for that side. We get a negative value for voltage. That means it's not spontaneous as written. So electrons would actually flow from this end to that end. They go backwards. Okay, let's answer the question. The cell reaction is spontaneous. No. We just said it wasn't. The cell reaction is non-spontaneous. Well, yeah. With a standard cell potential of minus 5.80. No, we don't add those two negatives together. We change this one to a positive. So the standard potential is actually 0.06, negative 0.06. The cell reaction is non-spontaneous with a standard cell potential minus 0.06. That's your answer right there. All right. Let's see. I want to tackle this one. Okay. That might have some value. Number 34. Page 0, standard conditions. The cell increase with increasing temperature. Okay. Let's look at it this way. We've got two applicable equations here. One is the Gibbs free energy equation. Delta G 0 equals delta H enthalpy minus T S. Okay? So that tells us that the reaction is spontaneous whenever delta G is negative. Has to be negative. Okay? The relationship of standard potential to delta G 0 is minus N times the Faraday constant times E0. Okay? So this still has to be negative to be spontaneous. All right, maybe that's not true, so let's remove that. Okay. Which of the following statements is true? Well, notice that these first three statements say increase in temperature, increase in temperature, increase in temperature. And then we have this choice, greater than 0 for all temperatures. Right? So let's see what happens with increase in temperature first, because A, B, and C all are predicated on an increase in temperature. So what happens with an increase in temperature? Well, if temperature increases, and this is positive, and this is positive, okay, what would happen? Well, as this one becomes greater, then the whole term with increases, it becomes more negative. So this one decreases, right? It trends toward the negative, right? You're more likely to find a spontaneous reaction here, okay? So if that decreases, this decreases, that means this has to increase, become more positive in order to make this one negative. This one has to be increased. So as the temperature increases, the electromotive force or the standard potential increases. Here we go. The E for the cell will increase with an increase in temperature. That is true. Right? It won't decrease. It will change. And delta G is not greater than 0 for all temperatures. Right? Because it could go negative eventually as the temperature increases. Right? So D is false. C is false. B is false. A is true. So E can't be correct either. So A is your answer. And it's based upon this relationship, these two equations. We can't use this one alone because it says nothing about temperature. Right? We can't draw any conclusions based on temperature because this equation doesn't have it. But this one doesn't have electromotive force in it either. So we need both of the equations to answer this question. All right. How about 35? Let me scroll a little bit so we can get 35 in there. There we go. All right. Now this one looks really complicated, but believe me, it's not. The standard free energies of formation of several species. So what does that mean? That first statement says that these values are the delta G zeros, standard free energies for each of these formations. All right. So what is the standard reduction potential of methanoic acid, or formic acid is another name for that. Formic acid, methanoic acid, same thing. So what is the standard reduction potential for methanoic acid in this aqueous solution? What we need to do is find out, all right, what's the standard free energy for that reaction? Because we have an equation that will give us E0. Right? E0 equals, well, actually, it's written this way first. Delta G 0 equals negative NF E0. We're looking for this one. So we need to solve it for negative delta G 0 divided by N in Faraday constant. So that's the one we want to use, because that's the relationship between voltage and free energy. But we need to find out what's the free energy for this reaction, right? So remember, all you have to do is say products minus reactants. Yes. So the delta G0 equals the sum of the delta G's for the products minus the sum of the delta G's for the reactants. Okay? So if we take the products, we need methanol and water. So there's methanol and there's water. Right? So the products would simply be minus 163 and then minus 237. Right? Because we only have one of each. Right? 163, 237. Right? And then we subtract the standard free energies of formation for the formic acid and hydrogen ions. Hydrogen ions are 0. Electrons are 0. So we really only have one. We just have the formic acid. Right? Formic acid is minus, there's only one of them. Like that. Okay? We don't have to include the hydrogen ions or the electrons. So this delta G0 then is equal to minus 48.8 kilojoules per kmol. I would expect, I think there's a term left out here. Standard free energy. Oh, that's kilojoules per mole. It's kilojoules per mole. Okay. So now we have this value right here and N. How many moles of electrons moved? We had to find out how many moles moved. Well, 4 right here in the balanced equation. N equals 4. So minus a minus, and the Faraday unit, let's write that in there first. Right? We have 4 here for the moles of electrons. And then a Faraday is 96,485 coulombs per moles of electrons. So this is moles of electrons. But this embedded within coulombs is the term of joule, not kilojoules. So this must be equal to 4.88 times 10 to the 4th joules per mole. Okay, so now once we resolve that, we get 0.126 volts. There we go. Okay. All right, that was 35. 35. Let's see, we want to mess with 36. Yeah, 36. I need to scroll that one. There we go. 36. All right. Now, those equations that we've used so far are still in useful information at the end of the document, which means they'll be at the end of the document of the exam. And if you take the exam online, that information is contained in a separate document. Well, actually, no. The way I'm doing it with this class is you'll download the PDF. And the PDF will have all of those equations at the end. Okay, so now we're looking at 36, and we have these equations right here, standard reduction potentials there. For a galvanic cell with these conditions, copper ions, lead ions, here we go, and then the metals, here we go. Calculate the maximum amount of work that would accompany the reaction of 1 mole of lead under standard conditions. All right. So where are we headed? Maximum amount of work for an electrochemical cell is related to the charge that moves times the maximum voltage. Okay? So what we need to do is find out what is the standard voltage. And that's what the E0 is. Under these conditions, for 1 mole of lead under standard conditions, what's the maximum amount of work? All right, so let's see. What's the cathode? The reduction? All right, which way do we arrange this one? If we make this one negative, it's not spontaneous because that's a negative summation. So this one has to be the anode. The cathode is going to be this one. Copper 2 plus 2 electrons yields copper metal. And that's 0.342 volts. The anode then is going to be the lead flipped. So now we're going to have lead on this side yields this one. And now the voltage is going to be 0.130. So overall the voltage, the total here is going to be, let's see, 0.472 volts. Okay? All right. So how do we know this value goes here? Right. What is that value? Q. Well, if we have 1 mole of lead, 1 mole of this gives up how many moles of electrons? All right. 1 mole of lead. And the relationship here is 2 moles of electrons for every 1 mole of lead. Right? So now we know how many moles of electrons, but Q, in this chapter, Q is not heat. This is not thermochemistry. Q is charge in coulombs. So we need the conversion factor. We need coulombs per mole of electrons. Right? 96,485. Okay. So that gives us a value of let's see, 1.9297 times 10 to the 5th coulombs. So that would be in here. 1.9297 times 10 to the 5th coulombs. This is volts. And volts actually is joules per coulomb. Joules per coulomb. Right? So that's why the coulombs cancel and leave you with joules, which is the unit of work. This is a negative. Right? So the maximum amount of work that we can extract from the system, which has to be a negative number in order to do that, is equal to minus 9.108 times 10 to the 4th joules. And our answers are in kilojoules. All right, so we have to convert that to kilojoules. So 10 to the 3rd gives us 10 to the 1st times this is 91.08 minus 91.08 kilojoules. That's the maximum amount, or 91.1, rounded off. There you go. Okay? Let's see, that was 36. Uh, 37. Six identical cells. I'm seeing which one of these would be worth stopping for. How about 39? Yeah, let's do 39. Oops. Just scroll that one. Okay. 39. Here's our system. Silver goes to silver plus, so it's oxidized, loses electron. Nitrate goes to NO gas, so it's probably reduced. And hydrogen doesn't change, oxygens don't change. Oh, we're also helped out, right? Here's the anode reaction, right, with this voltage. Here's the cathode reaction with that voltage, standard voltage. What's the equilibrium constant at 25 degrees? Standard temperature. So in order to calculate the equilibrium constant, we have to use the relationship where we need to know how many electrons are transferred. Right? Because we're going to use the Nernst equation. How many electrons are transferred? Well, all we need to do is match these electrons to those electrons. So 3 electrons here would give us that. So N equals 3 moles of electrons. Okay? What's the standard potential? Okay. If this is the anode already written for us, and this is the cathode, we just add them together. Right? So that value would be 0.1646 volts. Now here comes the important part. If this is the Nernst equation, That doesn't tell us K. But what do we know about K? I may have said earlier that the standard potential is 0. If I did, that's not right. At equilibrium, the standard potential is irrelevant. It's whatever it is. But the actual voltage of a system at equilibrium is 0. So that means under equilibrium conditions, that value is 0. There we go. Now we just solve for that K. If 0 equals 0.1646 volts minus 0.0591 divided by 3 times the log of K. Then we solve for K. We get down to this point. Log K, you can do this math yourself. Log K now is equal to 8.3553. So K is equal to what? K is equal to 10. Yeah, 10 to the 8.3553. That's the way logs work. Base 10, the power of 10 equals K. So solve that one out. Let's see. Let's go on out. 266 times 10 to the 8. So what does that mean? That K is huge, which is typical for galvanic cells. Very large K. Which means the equilibrium for this reaction is way to the right. Okay? That was 39. Let's see. More. Got more than I thought I had. Let's see. Let's try. There's some repetition here. All right. Let's look at 44. Just as a reality check. Remember what I've always said about word problems. Word problems are designed to confuse if you don't know the material. They will confuse you. So, look at this word problem. An excess of finely divided iron is stirred up with a solution that contains copper 2+ ions. So you've got iron, solid, and copper 2+ ions in aqueous solution. And they are not separated. Right? They're not separated into individual half cells. And the system is allowed to come to equilibrium. The solid materials then filtered off, and the electrodes of solid copper and solid iron are inserted into the remaining solution. Right? So after this has come to equilibrium, then we take solid copper and solid iron, insert them into the solution as separate cells. That's understood here. So we put maybe copper on this side, iron on this side, doesn't matter. Not for this discussion. And connect them and say, do we get a voltage? Right? What's the potential? The potential is 0. The key word here is equilibrium. Allowed to come to equilibrium. Okay? At equilibrium, the actual voltage is 0. That's the trick to this question. There's a lot of black ink up there. Most of it is unnecessary. The key is equilibrium. What's the voltage? 0. All right. How about, let's see here. This is going to take some work, but let's look at 49. There we go. Okay, you make a cell with an aluminum electrode in a solution of aluminum nitrate and a zinc electrode in a solution of zinc nitrate. If you increase the concentration of aluminum, which of the following is true about the cell potential? The potential will increase, decrease, stay constant, or cannot be determined. Or none of the above, which is kind of ludicrous, actually. Okay, how do we solve this problem? Well, let's sort of draw out our cells, half cells. So we have aluminum electrode in aluminum nitrate. There's aluminum, and here's aluminum nitrate. So we have there. Nitrate's a spectator. And then we have this solution, which is zinc nitrate. Zinc 1 plus nitrate. Is that right? Yeah, zinc is 1 plus charge. That's right. Okay. So there's your zinc. And now we connect them like that, and we have a salt bridge. Okay. Now, if you could increase the concentration of aluminum, so whatever the molarity of aluminum is, we're going to increase it. Okay, we need to know which cell is the anode and which cell is the cathode. So the standard potential for this one is, standard reduction potential is minus 1.66 volts. The standard reduction potential for this one, actually that's 2 plus, is minus 0.76 volts. So which one's the anode, which one's cathode? Well, if we make this one positive, we still got a negative summation. So we have to make that one positive. Right? So this one flips. That means this one is the anode. This one's the cathode. Okay? And the standard potential is, let's see, 0, 7 from 16 is 9. 0.90 volts. Okay. How many electrons are transferred? Well, we need to balance the equations first. So if this one's going to be written as an oxidation, we need aluminum yields, aluminum 3 plus 3 electrons. And this one is going to be written as a reduction. So zinc 2 plus 2 electrons yields zinc. Okay? So all we need to do is multiply this one by 3, and this one by 2. So if we multiply this one by 3, equals 2 aluminums plus 3 zincs yields 2 aluminum ions plus 3 zinc metal. Okay? All right. So what's the Q for this one? Well, the Q only needs this factor and that factor because these are solids. They don't count. So the Q calculation for this one is simply going to be concentration of aluminum 3 plus squared divided by zinc 2 plus cubed. Okay? So what happens if you increase the concentration of aluminum? If you make this one bigger, then the Q is bigger, correct? If you increase that one, then Q increases. You increase this one, Q increases. So let's look at that in terms of well, under standard conditions, 1 molar and 1 molar. If this is 1 molar and that's 1 molar, then the Q would be equal to 0. But if we increase this one above 1 molar, then this one is greater than 1. So Q is going to be greater than 1. All right, so let's look at the Nernst equation. I go back to the question. Which of the following is true about the cell potential? The actual cell potential, E. That's standard minus 0.0591 divided by 6. Actually, we don't need to know the electrons to answer this question. Times the log of Q. Okay, so if Q gets bigger, it's greater than 1, then the log of 1 is increasing, which makes this more negative. That makes this negative, which decreases that. Negative subtracted from this value decreases the value of the potential. So increasing aluminum will actually decrease your output voltage. It would decrease. Okay? Right. This one increases. This one decreases. Simply because increasing this makes that more negative. Okay, that was 49. Let's try, let's see. How about 56? Yeah, let's do 56. See if I can page to it. There we go. All right. How many moles of electrons are produced from a current of 14.4 amps in 3.2 hours? This problem is dimensional analysis, pure and simple. How many moles of electrons? That's the question. Moles of electrons. And we're given a current, which in physics classes, you learn that current is I, which is 14.4 amps. And time equals 3.20 hours. Okay. So what are we starting with? We're actually starting with amperage. 14.4 amps is equal to what? Well, an amp is coulombs per second. 14.4 coulombs per second. Okay? So one of the first things we can do is get rid of the time factor. So if we got 3.2 hours, 3.20 hours, that's not going to cancel seconds, right? So we need to convert hours to seconds, right? 60 minutes in an hour, 60 seconds in a 60 minutes in an hour, 60 seconds in a minute. 3,600 seconds per hour. So those hours cancel. Now we have those canceled. And we have coulombs at this point. Right? Coulomb is a measure of charge, but it doesn't tell us how many electrons. So we need to convert the coulombs here in the numerator to moles of electrons. Right? And 1 mole of electron is 96,485 coulombs. There we go. Now we've got moles of electrons. We've accounted for all of our units, and we now moles of electrons. So resolve that to 1.72 moles of electrons. Right there. All right, let's see. The next interesting one. Let's take this one step further. We're actually forming an electrolytic cell. See, which one was that? 64. There we go. 64. As long as you do not disobey chemical rules of any kind. This particular one is also unit conversion. But because I say chemical rules, I basically mean balanced equation. Because in order to answer this question, what mass of chromium could be deposited by electrolysis of an aqueous solution of chromium 3 sulfate for 145 minutes using a constant current of 11 amps? We need to know the relationship between the chemistry of the reaction, the electrolytic chemistry, and the applied current and how long it's applied. So what we're doing is we're taking this chromium in solution and we're in solution, what we have is this in solution. But the actual reaction is only this one plus 3 electrons yields chromium metal. That's the key. This is in solution. And this is the reaction that deposits the metal. Okay, so if we start off with 11 amps. That's what was being supplied in current. And remember, 11 amps is coulombs per second. So how long is it running? Well, 145 minutes won't cancel seconds. So we got to convert this one. Minutes to seconds. Right? So 60 seconds in a minute gives us that. How many moles of electrons? Okay, we got this one canceled, that one canceled, that one canceled. So we need convert coulombs to moles of electrons. Right? And it's 96,485, if my memory serves, coulombs per. So coulombs cancel. Go. Moles of electrons. Now we need the ratio of moles of electrons per moles of chromium. Right? So for every 3 moles of electrons, you get 1 mole of chromium. Okay? So now you know how to convert moles of an element to grams, molar mass. So I'm going to come down here, times moles of chromium, grams of chromium. And that happens to be, off the periodic table, 52.00. So now we've canceled that one, and we're left with grams of chromium. If we run all that out, 17.2 grams of chromium metal can be deposited under these conditions. Okay? Let's see. All right, the last, we're basically done. But in your review document, on the last page or two, here, short answer. What we have here is balancing these equations in either acidic solution, first 2, or the second 2 in basic solution. And we've already done that type of reaction, that type of balancing by half reactions. So I'm not going to go through these because it's the same procedure over and over again. Acid solution, and if you want to go basic, you just go acid and then convert acid to base, and you got it done. So that would be a lot of extra work for not much information. Okay? Well, it looks like I make it on time today. 10:50. I did make it on time. And since there's no lab, and we, of course, we won't be meeting. But the last lab report is due when? Better look it up. Chemistry. Well, actually, since the electrochemistry lab was canceled, then the complex ion lab was the last one we did, and it's due now. Okay, that's it. We're done. And All we have left to do now is the chapter exam on this. There's no final, just a chapter exam. On our next regular class meeting, which will be a week from today, Monday. Same time, same station.